Today, we're going to dive into a really fascinating physical puzzle. We're going to use a simple, homemade experiment to uncover a powerful, invisible force that, believe it or not, quietly shapes our modern world. So let's kick things off with a little mystery. Imagine you've got a small magnet spinning, just like a top. Now, what if you bring a simple coil of copper wire close to it? You're not even touching it, just getting it nearby. All of a sudden, with absolutely no physical contact, the magnet slows way down. So what in the world is going on here? To get to the bottom of this, we need to bring in the main suspects, two fundamental laws of electromagnetism. And they work together in this really elegant, kind of counterintuitive way to create this invisible braking effect.
Okay, first up, we have Faraday's law of induction. It sounds complicated, but here's the deal. As our magnet spins, its magnetic field is constantly moving and changing from the perspective of that copper coil. Faraday's law says that this changing field actually forces the electrons inside the copper to start moving. And moving electrons? Well, that's an electric current. It induces a current.
Now, this is where it gets really cool. This is the magic ingredient, Lenz's law. That new electric current we just made doesn't just, hang out. It creates its own magnetic field. And here's the kicker. The whole purpose of this new magnetic field is to push back, to oppose the very thing that created it in the first place. It actively fights against the spin of the original magnet. So you see, it's this perfect little chain reaction. The spinning magnet creates a current, and that current creates an opposing magnetic field that acts like a brake. The motion literally creates the very force that tries to stop it. It's like the magnet is creating its own worst enemy. But look, this isn't just some theory stuck in a dusty old textbook. As the source material shows us, you can actually see and measure this force with a setup that's surprisingly simple. So let's break down how they actually did it. And what's so great about this is it shows just how accessible science can be. You don't need some high-tech, multi-million-dollar lab. The experiment just uses a little motor to get things spinning, a magnet you could probably salvage from an old speaker, a coil of wire, and yeah, a computer or even your phone to do the measuring. And the method they used is it's brilliant. To measure the speed, they plugged the coil directly into the sound jack on a computer. That electrical signal the magnet creates, it gets recorded as a hum. The pitch of that hum tells you exactly how fast the magnet is spinning. So by doing this at different distances, you can precisely map out how strong that invisible brake really is.
All right, now for the evidence. This is where the physics gets real. This is the smoking gun. The entire mystery gets solved by looking at just one critical variable: distance. How far is the coil from the magnet?
Before we peek at the results, what do you think? What's your gut feeling here? As we slide that coil of wire closer and closer to our spinning magnet, does that braking force get a little bit stronger, or does it get way stronger? Let's take a look at the data. And wow, the results are pretty dramatic. At 10 centimeters away, the magnet's just humming along at full speed, 20 rotations per second, no problem. But then, look what happens when you close that gap to just 1 single centimeter. The speed absolutely plummets. We're talking less than 2 rotations a second. The magnet is basically crawling. That braking force gets incredibly powerful up close. And yup, this lines up perfectly with the report's own analysis. The slowdown isn't a gentle, gradual slope. It's a sharp drop. It's like the speed just falls off a cliff. The closer you get, that damping effect just gets exponentially stronger, way faster than you'd probably guess. So what this all means is there's a clear inverse relationship here. The closer you bring the coil, the more powerful that opposing magnetic brake becomes. This right here is the proof that our theory was right, that invisible brake is very real and its power is all about proximity. So, okay, we've solved our little mystery, but this whole principle, electromagnetic damping, it isn't just some cool party trick. This is actually a cornerstone of modern engineering and technology. It's a huge deal in the real world. This non-contact, wear-free braking force is used pretty much everywhere. It's what brings high-speed trains to a super smooth, silent stop. It's used to damp out unwanted vibrations in incredibly sensitive scientific instruments, like the seismometers that detect earthquakes. In fact, the way an electricity generator works is based on this very same resistance. Seriously, think about that for a second. The next time you're on a roller coaster and it just glides into the station at the end of the ride, perfectly smooth, perfectly silent, you'll know exactly what's going on. That's not friction, it's not magic. That is the elegant, invisible power of Lenz's law doing its thing. And this kind of brings us to one last thought. We've seen how this invisible brake works in a simple experiment, and we see it at work in the world all around us. So now that we understand how to control it, you have to wonder, what's next? Where else could we apply this silent, powerful, and totally frictionless force?